One of the toughest challenges in the asteroid redirect mission planning is to find a suitable target for us to explore. Now we're looking for a carbonaceous asteroid. What that means is it's similar in composition to carbonaceous chondrite meteorites, which are both the most ancient meteorites that we have seen in our collections back on Earth. They're the least altered from the era of the formation of the planet, so they preserve the history of the early solar system. Scientifically very valuable. But they also preserve, in many cases, water locked up in the clay minerals on these asteroids when they were formed. And this water can be baked out of the rocks of these carbonaceous asteroids, and using solar energy we can cook it out of the asteroid at fairly low temperatures, distill the water and use it for our life support or for rocket propellant purposes. So the suitable target has to be one of these carbonaceous type asteroids, and we can determine whether an asteroid has that composition first of all by sending a spacecraft to visit it. That's quite expensive. Instead, you'd like to use ground-based telescopes. Once you discover this pinpoint of light moving across the Earth's vicinity, then you train larger telescopes that can take a spectrum of the reflected sunlight from the asteroid, and that spectrum can be matched against meteorite spectra that we collect in the laboratory on Earth. And by matching the infrared spectrum of an asteroid and a suitable meteorite, we can then determine the composition, the rough composition of the asteroid target. Another qualification for the suitable target is its physical characteristics. How fast is it spinning? We can measure the light curve, the bright and dimming cycle of the asteroid in the telescope to determine its rotation rate. If it's spinning too fast, it might be too hazardous for astronauts to visit. So we want to choose an asteroid that's got the right spin rate. A third characteristic that's very important is the size. Our capture spacecraft can only handle objects that are 500 to 1,000 tons, something like 7 to 10 meters across. And so the brightness of the asteroid gives us an estimate of how large it is. And so we need to, of course, not go after an asteroid that's too big, and of course we don't want to waste our efforts on one that's too small to warrant the effort to retrieve it. So we fold in these physical characteristics, the spin rate, the size, the mass, and the compositional information that we get to choose and filter the candidate asteroids to the final handful that we'll want to visit. Right now I think NASA has about 3 to 5 candidates that might be suitable to visit in the 2020s that look like they're in the right mass range and composition. We need to expand that to several dozen candidates over the next 5 years. NASA is spending a little bit more money, on the order of $40 million a year, to discover suitable asteroids in the proper orbit for retrieval, and also to follow up and measure their composition and their physical characteristics. And that should increase the catalog of suitable targets by around 2018 to a number that enables the mission to proceed.